an explanation of the characteristic curves method for the midterm. First, we're going to look at the homogeneous case, which is where we have this term equals 0, and we just have a times the partial of u in the x direction plus b times the partial of u in the y direction. And we have u is a function of x and y, and then a and b can both be functions of x or y. And if we look at this equation, we can rewrite it as a dot product between the two vectors ab and ux, uy, and that has to equal 0. And we can notice that this is similar to the directional derivative formula, where we have a unit vector dotted with the gradient of a scalar function, and that has to equal, and that will give us the directional derivative. In this case, it's 0, which means that the derivative is 0 along the curve AB. And that's just what I'm saying here. So AB is the vector in the xy plane along which u of xy won't change. That's what it means for the derivative to be 0 along that curve. So we can imagine we have a curve here, and we're going to be tracing it out with a vector a and b, and along that we will not change the value. And this also means that the value of u is going to be a function of what curve we're on, because if we're on a curve, we're going to have the same value of u the entire time, and if we're on a different curve, we're going to have a different value of u, and we're going to use that later to actually solve the equations. So here we're going to define a function g of xyz, and we're going to say it's u of xy and subtract the height, which is z, and it's going to be constant. And u is also going to be constant because we're on a specific curve, because we're going to parameterize the characteristic curve as u of t, y of t, and z, where z is a constant, and u of t and y of t are just tracing out whatever curve that a and b are also tracing out. So that's going to be the characteristic curve. We're not going to have to deal with t later because it's all going to cancel out. So here we can see that if we take the derivative of g with respect to time, or respect to the parameter, we have this equation, which we'll notice is very similar to this, because here we have g and we take the partial with respect to x, and we assume that z is constant because it's on a characteristic curve. So all of that goes away, and we just have to compare these two equations, and this just came from the top. So here we have a of x and y is equal to, this is just the change in x with respect to the dummy variable. So this is going to be the rate of change in x as we move along the curve. And here is going to be the rate of change of y as we move along the curve. And then if we look at this graph, we can also, this is just the xy plane, so it's like this graph, but we're looking down from the top. And we can see that if we make a small change in x, that's the exact same thing as we were doing with a here. So it makes a lot of sense that the rate of change of x with respect to this dummy variable is going to be related to a. It's almost like we would just guess it if we were just looking at these two graphs. So here we can see that this dx dt is going to be the basically the velocity vector around this curve, because we have the position vector going from the origin to here. Then we have here is the velocity vector in the x component. Here's the velocity vector in the y component. And if we look at a and b up here, we just have this vector that we're tracing around is just ax hat plus b y hat, which is exactly what we get down here with the change of x with respect to t. So it makes a lot of sense that these are equal. And then this is the condition that we are actually going to be using to solve the problems. Now we can try to extend that to the non-homogeneous case, which is much harder to visualize, but we can just follow the math. We have this, except we have this e term, so we're going to flip it over, and then we're going to get a negative in this this vector formula, which we're comparing to the directional derivative. And here we're going to define g of xyz the same way, but now we have a curve where z is a param, where z can change with t. And then we're going to take our derivative here, and now we get that z is something, or this dz dt is going to be something, and then by comparison we can see that dz dt is equal to e, and that's what we have here. So instead of just these two equations, we're going to now have a third equation. So we're going to have to satisfy all three of these. These two are going to give us the curve that we're on, and it's going to give us like the form of the characteristic curves, and then this is going to compare it to this is just going to include the non-homogeneous part. So now we'll go through our practice problem to see how we actually get the solution from that condition we derived before, which is dx over a, and here e to the x squared is a, equals dy over b, and here x is b. So here is a equation to solve. We get integral e to the x squared negative x squared x dx equals integral dy. For this side we have to substitute, so let's say w equals x squared, and then dw equals 2x dx. So here we'll get integral e to the negative w dw, and then for this x dx we get 1/2 dw, so 1/2. And that equals y plus a constant. Now for this side we do 1/2, we'll have a negative e to the negative w, which is x squared, so e to the negative x squared equals y plus c1. I'll just move c1 over, still a constant, y plus 1/2 e to the negative x squared. Now our other condition was du equals 0. From here we just get u of xy equals a function of xy. This is our constant term because we integrated with respect to u instead of x or y, so it can be a function of x and y. And it will be, in fact, it will be a function of c1. And where do we get this? Well, we get that this is a relationship between x and y on the plane for a characteristic curve. This is specifically for a characteristic curve. We used it from which we got from the derivation. And if you look here, we're going to see that for each value of c, we're going to get a different curve. So we might move along here. We'll get a different characteristic curve for which the value of u is the same. And that's what it means for the value of u of xy to be a function of what curve we're on. This c1 is determining which curve we're on. It's the different relation between y and x for the curve. And u is just a function of that. So it's some dependency on that. It's not the same value, it's just a dependency. So we have a mapping from which curve we're on to the value of u because it's constant on that curve. So here we get u of xy equals some function of c1, which is y plus 1/2 e to the negative x squared. And this is our general solution, and we want to verify that it's true for this. So we'll have partial with respect to x. Rewrite this up. E to the x squared, u to the x. So we have ux equals f prime of y plus 1/2 e to the negative x squared. This is just the derivative with respect to the argument. So then we want the derivative of the argument with respect to x. So we get 1/2 times negative 2x e to the negative x squared. And then from here we also have this e to the x. So I'll put e to the x on both sides and these two cancel. And then for uy we get derivative with respect to the argument times derivative of the argument with respect to y, which is 1. And then we can put an x on either side to compare with the solution. And we see that this is going to be negative x f prime, and this is going to be positive x f prime. We're adding them together. We get 0 equals 0. This is a last second addition to the problem that was not in the original problem, but if we set u of x0 equal to e to the x squared, so we have an initial condition, we then get this equals e to the x squared, then we can substitute in s equals 1/2 e to the negative x squared, and then we get an expression for the outside in terms of s, and we can write f of s equals 1 over 2s, and then we get this is the actual solution based on this initial value condition, which isn't really what I want to show. Instead it's this, which is a plot of the general solution. So this is the thing we just derived, and here we can vary c, and then we'll plot the actual curve associated with this C1. And you can see as I vary C1, the line moves, and this is the characteristic curve that's associated with the problem, or with the specific U value. And if I move the plot over there, you can see very clearly that U is constant on this, because it's just moving a perfectly straight line up and down as I vary C. Here is the second problem, which I will do quickly. We get dx over 1 equals dy over 2x equals du over 2x. U here, in the original equation, this was negative, so the negative doesn't come here. This was negative e, so this is just e. So then we get the curve is dy equals 2x dx integrate x squared equals y plus c1. Here we're going to use x because it's easier to solve. 2x dx equals du over u x squared plus c2 equals natural log of u, and then we can have c2 in front, e to the x squared equals u of xy. So now we got to find what the c2 is, and I wasn't able to understand how we got this, where this is a function of c1. That's what it'll end up being. But the way you do it is you just plug it back into this equation. So if we take the partial of u, actually we'll say this is like v of xy or something, and we can say the partial with respect to u of this is going to be vx, and then e to the x squared, and then the other way that can go is v times 2x e to the x squared, and a plus this term, which is 2x vy, no extra term. We're going to have negative 2x times u, which is v times e to the x squared. And then when we start canceling terms, we're going to get that this goes away, we get vx e to the x squared plus 2x vy equals 0. And this is the exact same as this equation if we just got rid of this non-homogeneous term. So if we were to solve this, we would get v of xy is a mapping from C1, and this C1 is the same as this, because this part didn't use anything to do with du. This is just the homogeneous solution. So here, this is why the non-homogeneous solution is based on the homogeneous one. So then we can get u of x, y equals v times e to the x squared equals some function of this, which is y minus x squared. And that's going to have e to the x squared. So this e to the x squared will just cancel out this non-homogeneous term. Now we want to use the boundary condition u x 0. And then we'll get f of negative x squared e to the x squared equals x squared. So I'll just do a substitution, x equals negative x squared, so then negative s equals x squared. Function of s equals, so then we're going to have negative x squared on the right, which is just going to be positive x squared. So negative x squared becomes positive s on the right. So we have positive s, and then here we have times negative s. And this is our function u of xy then we get, so we just have to plug in this argument into this. So we're going to have negative y minus x squared, and then we'll have e to the y minus x squared, because these just go into these s terms. Then we'll have e to the x squared from over to the right. So here we have squared minus y. These e to the negative x squared and e to the positive x squared are going to cancel, so we get e to the y. And then I think I'm at 15 minutes. So to verify this, you just take the derivative and it equals 0. And I already checked it.